Good day, class. In this lesson, we will work on finding the instantaneous rate of change of a function. Before we dive too deep, I want to explain this formula to you because this formula is going to be very helpful. We'll see it very often and we'll deal with it to help us find the instantaneous rate of change. And think about that word instant. And so let's sort of talk about where this formula comes from. This can be read as the limit as h approaches 0 of f of the quantity x plus h minus f of x, all divided by h. We talked about this in a previous lesson, but notice how on the left, if I'm looking for the rate of change of a linear function, I can look at 2 points on that line and I can describe the change in y over change in x. No problem. For a nonlinear function, maybe I'm looking at the average rate of change for a segment of that function or an interval on that function. We talked about also in a previous lesson, maybe we'll be looking at an interval from 1 to 4, for example, and then I might observe the change in y over the change of x. However, if I'm dealing with the instantaneous rate of change, maybe I'm just looking at, instead of an interval from 1 to 4, maybe I'm really just looking at an exact location on that that curve, and I want to know what is the average rate of change in that instant. So this formula changes a bit from the formula we use for the average rate of change. Again, we have the limit as h approaches 0 of f of quantity x plus h minus f of x divided by h. And so we're still kind of in the groove of getting the change in y in our numerator, but something's slightly amiss here. We really need to know what's happening with that h. What is that? So let's look at that sort of graphically for a second. To really deal with this effectively, we need to be thoughtful about secant lines eventually becoming a tangent line. Let's say this is a secant line, the red line, and I'm trying to get to the instantaneous rate of change at 3. And so forgive me, this is a sketch, but if you can just kind of get the picture, since we're talking about very, very tiny changes that ultimately lead to becoming a tangent line. And I did discuss this in a different instructional video where I'm discussing secant lines and tangent lines. But even so, I have a secant line. It's becoming I'm getting to that tangent line. I want that tangent line at 3, where it's just touching the curve at 3. And so there are infinite number of secant lines here that are just where I'm getting closer and closer to that 3. Remember, I'm getting closer and closer, and I could be coming in from either direction, the left or the right. Here I'm coming in from the left, but I'm getting closer and closer and closer and closer. Imagine I could do this millions upon trillions upon billions of times, getting closer and closer to infinity, and eventually I get to the tangent line. And in that instant, what is my rate of change on this curve? So I can describe this formula, the formula for the instantaneous rate of change, as this f of x plus h piece being the function's value at the location of x plus some tiny little infinitesimal rate of some infinitesimal change amount. And so we'll see that a little bit more in a minute when we use the when we do an example. And then I can describe my f of h as the function's value. We're familiar with that one, my f of x. And then my h is the infinitesimal change in x. I'm getting close and close and close and closer to x, and we'll practice that in this course. In this example, we want to suppose the position of an object moving in a straight line is defined by this function, f of x equals 5x cubed minus 7x squared plus 8x, and we want to find the instantaneous rate of change when x equals 3. Now remember, we need to know where x is, or where that function, where the location on the x-axis is, in order to find the instantaneous rate of change. So I'm going to apply the formula that we've been given to find the instantaneous rate of change, and I'm going to substitute and off of an interval. I'm coming in from x plus h, wherever that h is, and I'm landing on x. And so I'll substitute these. My x is 3. And so I'll substitute this, and then in this particular example, I realize I have a little bit of convolution here, but that's okay. Please take a minute to pause this video here if you need to, and just kind of recognize where the 3 plus h has landed, and also where the 3 has landed. Moving right along, I also recognize I end up with a binomial cubed. Now the 3 plus h needs to be multiplied out. It's pretty easy to multiply out using the formula for a binomial cubed, or you can just multiply it out and just take your time. Even so, I want to apply that, and also the binomial squared, the 3 plus h quantity squared. So when you play this 3 plus h quantity cubed out, you're going to end up with this 27 plus 27h plus 9h squared plus h cubed. So just pay very careful attention to that. Also, I played out my binomial squared, and then my 8 just kind of came along with me. And then I simplified my f of x as well. Just to take a minute to go back, I have my f of x plus h. I have my f of x plus h here where I have made my substitutions. And then I have my f of x plus h here where I have played out those binomials cubed and binomial squared. Here I have my f of x. That's my y value of my function. When x is 3, because I'm going to substitute my 3 here, and then I have my value there. So all of this just kind of comes down to a little algebra and arithmetic, and so we end up here with some values that can be simplified. I'm going to cancel out these. If we combine these like terms, these constants actually go out. You'll see that pattern sort of happen over and over as you work through some similar example problems. And then I can also divide out some h's here. I'm looking for this. I want this to happen because that denominator of 0, if I try to substitute 0 in for my my h, I'm going to have some problems there with that 0 in the denominator. So I'll go ahead and cancel those h's. Fortunately, everything remaining is a canceled h. And then I can reveal, once I simplify here, what remains. I remain with the limit as h approaches 0 of 5h quantity squared, or 5h squared, forgive me, plus 93. And then we know that h is getting closer and closer to 0. So when it actually reaches 0, or I'm right up on my x, because my h is now no change, up to 0, then I'm left with 93, or 93, maybe it was units per second, I don't know, but this is a representation of my instantaneous rate of change, or my for this example. Here in my next example, I just want to deal with the trigonometric function here. We have f of x equals negative sine of x. Notice how I'm being asked the same thing, but it's outside of a real world problem. I'm just asked to find the instantaneous rate of change. So here I'm asked to find it at x equals pi. So maybe I want to be really thoughtful about this. What does negative sine of x look like in graph form? It maybe sort of looks like this. Maybe pi would be somewhere around here. This is a sketch. I'm just kind of putting this together so you can get some sense of what's happening. And then I want to apply my formula. In this case, my x is pi. And so here's what's happening. I'm coming in to pi. I'm getting to that pi, and I'm coming in from wherever, some very, very small quantities I'm coming in from. And so if I apply that formula to my function, I'll end up with this. Go ahead and pause this video, take a look and observe what has happened. How does this formula relate to what I now have? Moving right along, I can do some simplification here, because that negative sign of pi, according to the laws of trigonometry that we may be familiar with by now, is going to just become 0. So now I'm just left with the limit as h approaches 0 of negative sign of the quantity pi plus h. Now I can't just distribute this here, because we're talking about this negative sign of an angle. My angle is pi plus some amount. I can't substitute that h as for 0 as yet, because I have that denominator of 0. So I probably, in this case, I really don't have much of a choice. I just need to manually handle my h. So I'm going to look at h is 1, and I'll simplify and determine that value. I'll look at my h is 1/10. I'll look at h is 100th. I'll look at h is 1000th, and then I sort of discover, oh, I'm just getting 1 now. And as we continue in forever with those values of h, I'm just going to end up getting 1. that is my limit as h approaches 0. And so notice how that 1 went to 1/10, 100, 1000, and it can keep going, getting closer and closer to 0. And then I'm discovering that the limit is actually 1. And so that's going to be my solution, the instantaneous rate of change at x equals pi for this function.